Hello everyone, it's me, Professor Aaron Albert, here again with lesson 36. Let's learn some econ. So today we're going to take a slight tangent and we're going to talk about interest rates, discount rates, and how we can use these to figure out how our utilities adjust through time. And the application we're going to do with these, we're going to use these to show you that you can solve repeated games if they're repeated infinite number of times, and that the results are a little spicy, right? We're going to find some things that you might not have expected. Obviously, you can use discounting to determine how profits or utility transition through time in lots of contexts. But here's one. All right, so you're probably familiar with interest rates. Interest rates reflect the idea that if you get something later, it's worth less money because you can't get interest on it, right? If you take $100 and you find some bank that's willing to give you 10%, if you leave that $100 in that bank for a year, $100 today is worth $110 tomorrow. And you can see that in the function. Tomorrow's value, i.e. the future value, will be equal to the present value, i.e. how much it's worth today, times 1 plus the interest rate. So if I say you've got $100 and the interest rate's 10%, that means that the future value of $100 after a year at 10% would be $110. This could obviously be repeated, right? I could say you get 10% a year, and then you store it there for 5 years. You'd get 100 times 1.1 to the fifth, and so on and so forth. You could also invert this, right? Just divide by 1 plus I to the t on both sides, and you could solve for present values given some future value. That is, I'm going to be given $200 in a couple of years. How much is that worth today? So hopefully you've encountered calculations like this in your life. Either way, we're going to do things slightly differently. We're going to be dealing with what's called discount rates, not interest rates. Interest rates talk about the percent of money that you get over time for either borrowing or lending. Discount rates are going to reflect just kind of the relative value of future versus current money. I.e., a discount rate is how much less something is worth if you receive it later, because you had to wait. Usually it's between 0 and 1. So like, imagine that a Snickers bar tomorrow is worth half of one Snickers bar today. That would mean that your Snickers bar discount rate for you would be a half. I will note that if you're discounting due to interest rates or somebody's quoted interest rate and you want to calculate things in terms of discounting, you can just define a discount rate as just being 1 over 1 plus whatever the interest rate was from an interest rate problem. So we're going to do discounting because it makes the algebra a little easier in the type of problems we're going to do than if we were doing things with interest rates. With a discount rate, there's none of this 1 plus I shenanigans, where you just have to have deltas multiplied times each other, rather than 1 plus i's multiplied times each other. And the deltas are easy. Looking at present value and future value with discount rates, we have the following two functions. First off, note that the present value of some money received in the future is just how much money you're going to receive in the future times the discount rate raised to the power of however many periods. So, if you get $100 in a year, your 1 year discount rate is 0.9. That means that the present value of that $100 in a year would be 0.9. If you got that $100 in 2 years, it'd be 0.81. And so on and so forth. You can also take this present value function, divide by delta to the t, and find that the future value of something is just the present value times 1 over delta. This would be the idea that, well, how much is $100 today worth tomorrow? Well, if my discount rate is 0.9 again, it'd just be 100 divided by 0.9. So it's easy to talk about these things, but we should take a moment and make sure you guys know how to actually solve problems related to discounting. So here are 4 scenarios. For each, take a moment and see if you can figure out exactly what the valuations are being described. First, what is the value today of $10 received today and $20 received in 3 years? Also, what's the value today of $20 received in 3 years and $30 received in 4 years? Next, what's the value next year of $15 received today and $10 received next year? Also, what's the value next year of $20 received 5 years ago and $10 received last year? See if you can noodle those ones through and report back. Okay, welcome back. So what's the value today of $10 now and $20 in 30 years? Well, what's the value today of $10 today? That seems like $10. Plus we get $20 in 3 years. Look at my future value, my present value, and that says I should take the future value and times it by the discount. So that would be times 0.9 to the 3 for 3 years. Next, $20 in 3 years would just be my 20 times 0.9 to the 3 from before. Plus I get $30 in 4 years. So that'd be 30 times 0.9 to the 4th. Done. All right, these ones get a little trickier because we have some mixtures of present values and future values. Hopefully I don't mess it up. So what's the value next year of $15 today and $10 next year? Well, next year and next year are both the same time period, so it looks like the 10 is still going to be 10. Plus I get $15 today. $15 today next year should be worth more because I'm waiting on it. So I want to make this worth more money. To make it worth more money, I should be dividing it by 0.9. Similarly, $20 5 years ago next year means I've had 6 years to sit on $20. That should be $20 divided by 0.9 to the, I believe, 6 years are transpiring. Plus next year, if I get $10 last year, would mean I have $10 that I've sat on for 2 years, so it should be 0.9 to the 2. Again, hopefully I got those right. If not, you can go ahead and flame me in the comments. Sweet. Moving on. We can also do slightly interesting things, like repeated payments. For instance, see if you can write a formula or a summation for me that describes the value today of receiving some F dollars every year for some T years. I.e., let's make it real concrete. Let's say you get $10 every year for 100 years, and we're going to discount this with some discount rate D. What's that worth to you? Well, let's say this year I get $10, plus next year I get $10, plus the year after that I get $10, plus the year after that I get $10. It looks like we're going to have a summation. And now, it's worded ambiguously, so let's say that the first period is today, hence I get $10 today, it doesn't start next year, and let's say that it ends after, let's call it capital T years. I would just have 10 D little t, i.e. I get $10 plus 10 to the delta squared, all the way until I have 10 delta capital T. Simple. However, sometimes these summations don't really give you all the answers. For instance, how much value would you place on getting, let's say, $10 every year forever? Well, I could start with writing the sequence. I'd have 10 plus 10 delta plus 10 delta squared plus. But this is going to go on for a while, so let's cut to the summation. I would have t equals 0 to infinity of 10 delta to the t. And again, this seems like it's going to be worth infinite dollars, right? However, surprisingly enough, this actually turns out to be a geometric series. I would never expect anyone to have thought of this. However, with some clever math, it's quite apparent to see this. So first off, we've just shown that the present value itself is just f plus df plus d squared f plus d cubed f plus, and so on and so forth. Let's also consider something which is not apparently useful, but is actually the entire problem. Let's also consider what the present value would be divided by delta. Well, PV divided by delta would just be this entire series divided by delta. So I'd have f divided by d. D times f divided by d is just f. D squared times f divided by d is just d. So after you've noted these two bits, consider PV over d minus PV. Well, this term's going to cancel. This term's going to cancel. This term's going to cancel. Everything cancels except for the f divided by d term. With this in mind, we can note that PV divided by d minus PV equals f divided by d. And now, this is cool and all, but the important thing is we want to know the value of PV. We want to know the value of the present value of the infinite stream of payments. If you do some algebra, you can find that the present value of any infinite stream discounted, as we've been doing, is just going to be f, i.e. the value you get every period, divided by 1 minus d, the discount rate. So if you remember this, you can instantly solve all infinite series problems. Speaking of infinite series problems, let's think of some repeated games. So here is a game that hopefully from its structure is instantly familiar. Take a moment, think it through, see if you can find for me 1. The Pareto optimal box or boxes. 2. The Nash equilibrium box or boxes. And then report back. Well, hopefully you've noted that if we're on the bottom row, player 1 is going to want to play up. Right? They're going to go from -1 to 1, that's no good, and 1 to 2. So it looks like up is dominant. Similarly, if you're in the right-hand squares, either of them, you're going to go left. So it looks like up and left are dominant. So this is the Nash equilibrium. However, that's unfortunate because that's the only square in this game that is not Pareto optimal. Right? I can move from here to here and make everyone better off. Also, you should note that these are also Pareto optimal, but the important thing is that this 1 squared is strictly better for both players, but game theory tells us it will never be reached because the Nash equilibrium is 0, 0. So if we get 2 people together and they play this game, they're going to play 0, 0. That is the only equilibrium. And that's sad because if they had played differently, if they played not equilibrium strategies, not smart strategies, they'd end up playing 1, 1. I.e. they'd play downright and get 1, 1. Moreover, we won't get into finitely repeated games, but I will tell you, in passing, that they're not interesting. Right? We learned when we did these game tree things, how do we solve these things? We start at the bottom. So let's say I play this game twice. Play it once. Player 1, player 2 both go. And then I play it again. Player 1, player 2 both go. How do we solve that? We start at the bottom of the tree. So the bottom of the tree is going to be playing this game. And when they play this game at the bottom of the tree, it's as though they're playing it a single time. So that means the last time they play this game, they're going to play the Nash equilibrium, i.e. 0, 0. And since they know they're going to play this 0, 0 the last time, there's really no room for either player to punish each other or promise they're going to play 1, 1 or anything. Right? At the end of the tree, they're going to play the Nash equilibrium because that's how we solve these games through backwards induction. And if you're going to play 0, 0 in the last game, you're probably going to play 0, 0 in the second to last game, and all the way up the tree. It's 0, 0s all the way down. Why? Because again, with backwards induction, we start at the bottom of the tree. The bottom of the tree, you must do equilibrium, and the equilibrium here is 0, 0. All right. So this, as a one-time game, we'll play the Nash equilibrium. As a finitely repeated game, you still have to play the equilibrium. It's going to be 0, 0 just a bunch of times. However, what happens if we play this infinite times? Well, if we play this infinite times, since there's infinite times they're playing this game, there's infinite possibility of infinite strategies, they could do all sorts of crazy things. One interesting thing they could do is play what economists call the Grim Trigger strategy. The Grim Trigger strategy is described as thus. Both players are playing a Grim Trigger is if they agree the first time they play this game, of all infinite times, that they're going to play down and right. Then, if you're not in the first stage, look at all of the previous times you've played this game. If every time you've played this game, everybody has played appropriately to get the 1-1 outcome, that is, if your player 1, you've played down, and player 2 has played right, keep playing 1-1. However, if at any time you look at this game, and there's anything other than 1-1 as any of the outcomes ever, play 0-0 forever. That's why it's called the Grim trigger. It works. You play 1-1. If there's ever any deviation at all, any little deviations, you are both dooming yourselves and each other with 0-0 forever, which is quite grim, and it has been easily triggered. So the question is, well, for what levels of D, our discount rate, can we sustain this cool Grim trigger strategy whereby they get 1-1 forever, right? We just proved that this game, if repeated once or twice or 3 times, you'll get 0-0. If we repeat it infinite times and we have the right deltas, we can promise 1-1s forever. And that's great. We found a reason and a way to get cooperation. We just need to play a game infinite times. So in order to find out if and over what deltas this can be sustained, we have to compare the payment streams. So this time, you must ask yourself 2 questions. 1, assume your player 1 is a symmetric game, we only have to solve it once. What is the total discounted payoff of playing D and R forever? And what is the total payoff if you deviate in the first period instead? Well, if we play down and right forever, what do you get in the first period? 1. What do you get in the second period? 1. What about the third period? 1. You have 1 every period. All we have to do is discount it. We're going to get 1 plus delta squared, plus delta cubed, all the way through. And we just saw 2 slides ago that this simplifies to 1 over 1 plus delta. So that is our payoff if we cooperate, if we play nice, if we play the nice boy strategy the entire game. Next, what happens if we deviate? Well, if we deviate as player 1, we would play not down, but up. If we play up, we'd get 2. Cool. We bamboozled player 2 once. We got this juicy 2 payoff. But what happens in the next period? Well, player 2 observes we didn't play nice in phase 1, so they're going to play 0. Also, we observe that we didn't play nice in phase 1, so we also will play such that we get 0. So if we deviate, we're going to get 2 plus 0 times delta plus 0 times delta squared plus, and so on and so forth. It's just 2. So you might note that this makes for an easy comparison. We will cooperate so long as 1 over 1 minus delta, i.e. our payoff from playing the nice guy strategy, is better than the payoff for deviating, i.e. 2. So if 1 over 1 minus delta is greater than 2, that means we can sustain 1s forever as long as our discount rate is greater than half. That is, as long as tomorrow $1 is worth more than 50 cents today, we can sustain this great cooperative strategy. You also might ask, well, what happens if I were instead to deviate in the second period? You'll notice if I deviate in the second period, I'd get the 1 from cooperating in the first period, plus 2 times delta, i.e. I didn't cooperate, plus 0 forever. Anytime you deviate in any period except for the first one, you're going to get even a small payoff, right? 1 plus 2 delta should be smaller than 2 delta. Than just 2. As long as our deltas are not super big. So the important thing is, if we ever were going to want to deviate, it'd be best to do it in the first period. So check the first period, ignore all other incidences where maybe I deviated the 1,100th time I played this or some other weird thing. So now that we know how to solve for Grim trigger strategies in an infinitely repeated game, as always, I'll leave you with my favorite thing, an independent exercise. So here is a new game that has the same exact format of the game we just solved. Go through and find for me, 1, the total discounted payoff of playing down and right forever, i.e. the cooperate outcome payoffs. 2nd, find the total discounted payoff of deviating in the first period. We'll assume that if they ever deviate, they would deviate in the first period. That's probably what's best for them. And then, using the results from this and this, tell me what values of down and right, what values of delta can sustain this down and right forever strategy. Good luck. Let me know how you do. Thanks so much. See you next time.